Hi everyone. Today we're going to be completing our notes on applications of vectors. I want to start off with this definition for velocity. Velocity is a vector. So velocity of a moving object. And that object could be a plane, it could be a boat, it could even be like the wind. Velocity of a moving object is modeled by a vector whose direction is the direction of motion, and whose speed, or whose magnitude, is the speed. So remember that vectors have both magnitude and direction, so therefore the magnitude of a moving object, or magnitude of the velocity, is the speed, and the direction of the vector, the velocity vector, is the direction of motion, and often that'll be given using bearing notation. All right, so I want to try this first example. An airplane heads due north at 280 miles per hour. It experiences a 38-mile-an-hour crosswind flowing in the direction 60 degrees east of north. So we're going to start by drawing the airplane vector. I'm going to draw my bearing, north, south, east, and west. And I know that it's going due north at 280 miles per hour. So I'm going to draw that due north. And I'm going to label that 280 miles per hour. I also know that the crosswind is going at a direction 60 degrees east of north. And the magnitude is 38 miles per hour. So I'm going to go ahead and draw that as well. So we have 38 miles per hour is the magnitude of that wind vector. And the direction is 60 degrees east of north. So that's going to go east of north. Okay? Now, we want to find the true velocity of the vector in terms of the unit vectors I and j. And we want to find the true speed. Okay? So in order to do this, we need to find the resultant vector, or the sum of the airplane and the wind vectors. So when we draw this, we're going to draw this as two vectors tip to tail, and then we're going to draw the resultant vector from start to finish. So I'm going to take this wind vector, and I'm going to put it at the tip of the airplane vector. So I'm just going to duplicate that vector, 38 miles per hour, in the direction 60 degrees east of north. The resultant vector I'm going to denote with a dotted line, and that's going to be going from the start all the way to the end of the wind vector. Okay, so this is what we're solving for. Let's go ahead and label some of these vectors. The first vector I'm going to call vector u. And I'm going to say let u be equal to the velocity of the airplane. And then let vector v, remember these are bolded vectors, represent the velocity of the wind. And so what we're solving for here is going to be u plus v, the sum of these two vectors. And that's going to be the true velocity of the airplane. So after all of the wind blows the airplane in the direction, it's going to affect the path of travel for the airplane. Okay, so we're going to find u plus v. All right, so let's go ahead and label what is the component form for vector u, the velocity of the airplane. Well, it's going due north, and so the horizontal component is 0. It's not moving right or left at all. And then the vertical component is the vertical speed, 280 miles per hour. And so the component form for the airplane is 0, 280, or in unit vector form, just 280j, where j is the unit vector 0, 1. For the wind, again, bold vector v, component form here, well, we know that the horizontal component, if I were to look at this triangle right here, if I were to draw this as a triangle, the hypotenuse is 38. I want to find the horizontal component, delta x, and the vertical component, delta y. And in order to do that, I need to use this angle right here, the reference angle. Because it's 60 degrees east of north, this angle formed in the triangle here must be 30 degrees. That's formed with due east. Therefore, the horizontal component must be 38, the hypotenuse, times the cosine of 30. We can get that using right triangle trig. Again, cosine of 30 is adjacent over hypotenuse, or x over 38. Therefore, x is equal to 38 cosine 30. And in pretty much every case, when we're finding the component form for vectors, it's basically going to be the magnitude times the sine or cosine of the angle. Okay, so in this case, we know the cosine of 30 is the square root of 3 over 2. And so we have 38 times the square root of 3 over 2, which is equal to 19 square root of 3. And so the horizontal component for the wind has a magnitude of 19 root 3 miles per hour. Now we need to find the vertical component, y. And so again, using right triangle trig, delta y is equal to 38 sine of theta, or sine of 30. Now we know what the sine of 30 is. It's 1/2. So this is 38 times 1/2, which is equal to 19. And so therefore the component form for the wind, vector v, is equal to 19 root 3, comma 19. And using unit vectors, this is equal to 19 root 3 I plus 19 j. And again, I'm bolding those vectors I and j. Okay. So then the resultant vector, u plus v, and this is the answer to part A, is equal to the sum of the horizontal components, so 0 plus 19 root 3, and so that's just 19 root 3, I, and then plus the sum of the vertical components, 280 plus 19, which is equal to 299 j. And so the answer to part A, the true velocity of the plane, again, is a vector, velocity is a vector, is this vector here, 19 root 3 I plus 299 j, where I and j are the unit vectors. You could also write this in component form, 19 root 3, comma 299. So let's go ahead and circle this answer for part A. Now part B is asking for the true speed and direction. So we need to find the magnitude and direction of this vector, the velocity vector. So part B, I'm going to use some of this space over here. So in order to find the speed, speed is just the magnitude of the velocity. It's the scalar of the velocity, just the magnitude. So we're going to find the magnitude of the resultant vector, u plus v, which is equal to, using our magnitude formula, the square root of the quantity 19 root 3 squared plus 299 squared. And from here, if you have a TI Inspire, you can just plug it right into your calculator and evaluate. 19 root 3, the quantity squared, is equal to 1,083. And 299 squared is equal to 89,401. Okay, when we add those together, we get square root of 90,484, which is equal to 2 square root of 2,262, which is approximately 300.8 miles per hour. And so that tells us if the plane is flying at 280 miles per hour due north, experiencing this crosswind, the true speed is going to be 300.8 miles per hour, which I always do that check. Does this answer make sense? Yes, if the wind is pushing it forward north and east, it's going to accelerate the plane. It's going to be traveling a bit faster. Okay, to find the direction, so we found the speed, we need the direction. Take a look at our diagram here. What we can solve for is the direction, theta, which is the inverse tangent of the opposite over adjacent. Okay, so looking at this resultant vector, the opposite would be this vertical part, and the adjacent would be this horizontal part of this resultant vector. If we were to draw out the triangle, theta would be that angle right here. Okay? So the direction is equal to the inverse tangent of the opposite, or the y value, 299, over the x value, the adjacent, 19 root 3. And if you were to plug that into your calculator, you would get about 83.7 degrees. Make sure you're in degrees mode. Now again, remember that I just found this angle right here. So in order to express our direction in bearing notation, we need to find this little angle up here. And so we're going to subtract that from 90 to find that little angle there. And so the complement of 83.7 is about 6.3. So I'm going to take 90 minus 83.7. We get about 6.3 degrees. And so the direction, the true direction of the airplane is 6.3 degrees east of north. And this is our answer. Okay. All right. Let's try another one. Go ahead and flip the page. So example 12. Example 12 states a straight river flows east at a speed of 10 miles per hour. A boater starts at the south shore of the river and heads in a direction 60 degrees from the shore. See the figure below. The motorboat has a speed of 20 miles per hour relative to the water. We need to find the velocity of the river. We need to find the velocity of the motorboat, the true velocity of the motorboat, so that's including the river, and then the true speed and direction, similar to the last problem. So let's go ahead and start with part A, asking for the velocity of the river in component form, or I and J. So I'm going to say let U be the velocity of the boat, and then I'm going to say let vector V be the velocity of the river. Okay. All right, so finding the velocity of the river is the vector V. Once we've defined our variables, we can go ahead and find that. So we know that the river is flowing east at a speed of 10 miles per hour. And so therefore, there is a horizontal component of 10 miles per hour in the positive direction because we're flowing east. And then because it's due east, there's no vertical component. It's just 0. And so the vector V, the velocity of the river, is 10, 0, or 10I using the unit vector. For part B, the velocity of the motorboat relative to the water is just the velocity of the boat, so not including the river's effect on its path of travel. So vector U is the velocity of the boat. We know that in component form, it is the magnitude times the cosine of the angle, and then the magnitude times the sine of the angle. And so if we're looking at the boat here, it is making an angle of 60 degrees with the shore. And so this is going to be the angle that we're using. Okay, it's always made with the horizontal. Because it has a speed of 20 miles per hour, we're going to take the components, 20, cosine of 60 for the horizontal component, and then for the vertical component, it's going to be 20 sine of 60. Again, using right triangle trig, where the cosine is adjacent over the hypotenuse, or delta x over the magnitude. And then likewise for sine, we have the opposite over hypotenuse, which is the delta y over the magnitude. Okay, let's go ahead and evaluate these. We know what the cosine and sine of 60 are. And so we have 20 times, well, the cosine of 60 is equal to 1/2. And then comma, the sine of 60 is root 3 over 2. So 20, and then times root 3 over 2. So therefore, the component form for the boat is equal to 10, comma, 10 root 3. If you were to use unit vectors, we would have 10I plus 10 root 3j. Part C. Now we're looking for the true velocity of the motorboat in terms of I and j. Okay? So we're going to find the resultant vector, u plus v. So we're going to add the component forms of these. So u plus v is equal to the horizontal component, 10 plus 10, or 20. And then the vertical component, 0 plus 10 root 3, which is just 10 root 3. We're just adding those two. Now it asks for it in unit vector form, so this is equal to 20i plus 10 root 3j. Okay. Finally, part D is asking for the true speed and direction. So again, we're going to find the magnitude and direction of this vector that we just found, the resultant vector. And so the speed is equal to the magnitude of u plus v, which is equal to, using our magnitude formula, delta x squared, or 20 squared, plus delta y squared, or 10 root 3 squared. Let's see. 20 squared is 400. 10 root 3 squared is 300. And so we get the sum, square root of 700, which is equal to approximately 26.5 miles per hour, which again makes sense in this context because we're looking for, like, the river is kind of helping the boat go a little bit faster. I'm expecting our answer to be a little bit faster than 20 miles per hour. So 26.5 makes total sense in this context. Let's also find the direction, which again is equal to the inverse tangent of delta y over delta x. And so we have 10 root 3 over 20, which if you were to plug that in your calculator, you would get about 40.9 degrees. Now again, that gives us that angle formed with due east, or like that reference angle. And so we need to subtract that from 90. So 90 minus 40.9, this is the complement, which is equal to 49.1 degrees. So using bearing notation, we have 49 degrees east of north. And so this is the true direction of the boat. Okay? This has been our notes on applications of vectors. We're going to get a whole lot of practice, so we'll see you tomorrow. Have a great day, everybody.